Your weather app says there is almost no chance of rain. You leave the house without an umbrella. 20 minutes later, you are standing under the awning of a closed shop while water runs off your jacket. The app still shows a little gray cloud. No rain. At that moment, weather forecasting can feel less like science and more like a very expensive guess. The strange part is that modern weather forecasts are much better than they used to be. The Met Office says its 4-day forecast is now about as accurate as its 1-day forecast was 30 years ago. Satellites scan the atmosphere, weather balloons measure temperature and humidity high above the ground, radar watches rain develop, and supercomputers solve enormous sets of equations. ECMWF, one of the world's leading forecasting centers, runs global models several times a day. So why can your Tuesday afternoon forecast still be badly wrong? Because a forecast has to solve two different problems. First, it has to estimate what the atmosphere looks like right now. Then it has to calculate what that atmosphere will do next. Both steps contain uncertainty, and the second step can magnify tiny errors from the first. At 7 a.m., a weather station may tell us the temperature, pressure, wind, and humidity at one location. A balloon can sample the air above it. Satellites add huge amounts of information over oceans and remote regions. Aircraft and ships contribute more observations. But nobody measures every cubic meter of air on Earth. There are gaps between instruments, gaps in time, and variables that are measured indirectly. Before a forecast even begins, the model is working from the best reconstruction of the atmosphere we can make, not a perfect copy. That sounds minor, but it matters. The atmosphere is chaotic. In a chaotic system, two starting conditions that are almost identical can evolve into noticeably different outcomes. This is the idea associated with Edward Lorenz and the famous butterfly effect. It does not mean a butterfly literally creates a storm. It means that small uncertainties in the starting state can grow as the forecast moves forward. You can see this when a storm track changes between forecast runs. On Monday morning, a low-pressure system may be predicted to pass north of a city on Friday. 12 hours later, new observations enter the model. The starting picture changes slightly, and the predicted track shifts south. The forecast did not suddenly become stupid. It was recalculated from a slightly different estimate of reality, and several days of chaotic atmospheric evolution amplified that difference. A second problem sits inside the computer itself. Weather models divide the atmosphere into a three-dimensional grid. They calculate wind, pressure, temperature, moisture, and many other variables from one time step to the next. But the grid is not infinitely fine. ECMWF's medium-range ensemble, for example, operates at roughly 9-kilometer horizontal resolution. Some regional models go much finer. The Met Office runs a high-resolution UK model with grid boxes around 1.5 kilometers across in its inner domain. Even 1.5 kilometers is enormous compared with many things that affect the weather around you. A row of buildings, a forest edge, a small valley, a warm supermarket parking lot, a narrow lake breeze, or a single growing thunderstorm can all exist at scales smaller than the model can fully represent. The model has to simplify some processes and estimate their average effect. Meteorologists call this parameterization. Clouds are a good example. Inside one model grid box, air may be rising in one place, sinking in another, forming cloud here and staying clear a few kilometers away. The model has equations for cloud formation, condensation, ice, radiation, and convection, but it cannot track every droplet. This is one reason precipitation is often harder to forecast at one exact point than something smoother, like the general temperature pattern over a region. At 4:10 p.m., a summer shower forms over the western side of a city. The model predicted that the atmosphere would be unstable and that showers were likely. Good. But it placed the strongest cell 15 kilometers east of where it actually formed. People under the real shower say the forecast failed. People under the predicted shower location stay dry and say the same thing. The large-scale forecast can be mostly correct, while the experience at individual addresses is completely wrong. This gets messy fast with thunderstorms. A small difference in low-level moisture, cloud cover, or wind can affect where the first strong updraft forms. That storm then changes the air around it. It produces rain-cooled outflow, modifies local winds, and can trigger new storms nearby. Once convection starts, the storm is no longer just responding to the environment. It is helping create the environment for the next storm. Forecast apps make another compromise. They compress uncertainty into a tiny interface. A phone screen may show one temperature, one rain icon, and one wind number for 3 p.m. The underlying forecast system may contain dozens of possible scenarios. ECMWF's medium-range ensemble uses 51 forecasts, one control run, and 50 additional members with slightly altered initial conditions and model behavior. If the members stay close together, confidence is higher. If they spread apart, the atmosphere is telling us that several outcomes remain plausible. But a little rain icon does not show you that spread very well. 2 days can receive the same icon, even if one has a tightly clustered forecast and the other has enormous uncertainty. One app may choose the most likely scenario. Another may blend several models. A third may update at a different time or apply its own post-processing. You check 2 phones at breakfast, and they disagree by 3 degrees and 2 hours on the rain. That does not necessarily mean one company has discovered different physics. They may simply be turning probabilistic model data into a simple consumer forecast in different ways. There is also a mismatch between what forecasts are good at and what people remember. If the temperature forecast is 21 degrees and the afternoon reaches 22, nobody tells friends about the incredible success of numerical weather prediction. If the app says dry and a 10-minute shower soaks the laundry, that error is memorable. Weather is judged by inconvenience. The forecast horizon matters too. Tomorrow's broad weather pattern is usually much easier to predict than the exact weather 10 days from now. NOAA gives a simple public rule of thumb. Forecasts around 5 days are much more reliable than forecasts around 10 days. Exact accuracy depends on what variable you measure, where you are, and what counts as correct. So there is no single percentage that describes every forecast. Still, the direction is clear. As lead time increases, uncertainty grows. This is why a detailed icon for 11 days from now can be misleading. The model may still have useful information about the broad pattern, perhaps a higher chance of warmer than normal conditions, or a greater risk of unsettled weather. It usually has far less skill in telling you that rain will begin at 2 p.m. in your neighborhood. Long-range forecasts become more useful when they talk in probabilities and patterns, rather than pretending to know the exact hour. A forecast can also be technically correct and still feel useless. Suppose there is a 60% chance of rain and it stays dry. That outcome does not prove the forecast was wrong. A well-calibrated 60% forecast should sometimes produce rain and sometimes not. The only way to judge it properly is to examine many similar forecasts and ask whether the event happened roughly as often as the probability suggested. Humans are not naturally good at evaluating repeated probabilities. We experience one barbecue at a time. Fine, but forecasters do make genuine errors. Models can mishandle cloud, soil moisture, snow cover, fog, convection, or the timing of a front. Observations can be sparse or noisy. A regional model can inherit a bad large-scale pattern from the global model at its boundaries. And sometimes several ensemble members agree with each other and still agree on the wrong answer. Confidence is not the same thing as certainty. The good news is that forecasting keeps improving. Better satellites provide more detailed measurements of temperature and moisture through the atmosphere. Higher resolution models represent coastlines, mountains, and storms more realistically. Data assimilation has become far more sophisticated. Ensemble forecasts expose uncertainty instead of hiding it, and newer machine learning systems are now being run alongside physics-based weather models at major forecasting centers such as ECMWF. They can improve speed and skill in some areas, but they do not remove the basic problem. The atmosphere remains chaotic, and never perfectly observed. So the next time your weather app changes from sunshine to rain and back again, the change itself may be useful information. It can mean the atmosphere is sitting near a fork, where small differences produce different outcomes. Check the probability. Look at radar when the event is close. Pay attention to forecast confidence if your service provides it, and treat precise details several days away with less confidence than the general pattern. Weather forecasting is not failing because meteorologists lack equations or computers. In many ways, it is one of the most successful prediction systems humans have built. The difficult part is that we are trying to predict a moving, three-dimensional fluid covering an entire planet from incomplete measurements, while tiny errors grow with time. And then we ask the result to tell us whether it will rain on one particular street at 4:15 in the afternoon. Sometimes, getting the atmosphere mostly right is still enough to get your jacket completely wrong.
Thanks for watching! If you enjoyed the video, please like, subscribe, and leave a comment below. See you in the next one!